Let's continue our discussion of analog to digital converters by taking an example. Okay, so we'll take an example signal and try to convert this analog signal into digital signal and look at what are the steps that are involved in doing that. So we talked in the previous video about quantization, right? Quantization is taking the analog signal uh, or the analog input or the ADC range and dividing the ADC range into the number of available levels. And in this case, we assume that we have a 3-bit ADC and therefore 2 to the power 3, that is 8 available levels. Now, a 3-bit ADC is almost you don't use a 3-bit ADC, okay? Because the errors that are associated with a 3-bit ADC is quite a lot. Maybe around 8 to 10 bits, sometimes even 16, 32 bits might be used. But anything, usually, I would say something like 8 bits would be the minimum number of levels uh, that we use. But in this video, I'm using 3 bits just so that we can see it more clearly. Okay, so so one of the steps in the ADC we said is quantization. So let's take, for example, this signal. So the signal here is analog signal, and we want to convert this analog signal into digital signal. Okay. Now the first step to do is not quantization, because we could do quantization, but doing quantization, we still have infinite number of points on the time axis, right? And you want to reduce that before you do quantization. So the first step that we do, therefore, is called sampling. And sampling is basically taking the signal at some uniform time interval and just keeping these points with us while ignoring the rest of the signal. Okay, so let's say the sampling interval is given by this time t, and the points that we get after sampling are these points. So again, just to repeat, what is sampling? Sampling is just picking up points at an uniform interval in time. Okay, and once you do sampling, you will have a signal like this. Okay, that is left. You ignore the other signals. Now you may say, well, that seems to lose quite a lot of information from our signal, and you will be right if you don't choose your time interval properly. But if you choose your time interval well, and then you can have a lossless transition from the analog signal to the digital signal. And the condition that gives us lossless signal is given by this equation in the red box here, which is called the Nyquist criterion. So in this case, F signal is the frequency of the signal, the maximum frequency in the signal, and F sampling is the frequency of sampling. Okay, you can write this in terms of the time interval as well as it is written here. So if your sampling frequency is greater than twice the maximum frequency in the signal, then you can reconstruct from these sampled points the complete signal without any loss. Okay, and I would just ask you to take this on faith for now from me, and maybe in the subsequent courses that we do, we'll learn how this works and go a little bit to more towards a proof of this criterion. Okay, so the first step that we want to do when we are converting from analog to digital conversion is sampling, and we sample to prevent any errors or lose data. We sample according to the Nyquist criteria, which states that the sampling frequency should be greater than equal to twice of the signal frequency. And if we do that, we end up with a sample signal which looks like this. Okay, you can see that now we have discretized the time axis, right? We have not discretized the amplitude axis yet because it can take any values in between these levels as well. And that's what we are going to do next, and that's called quantization. So next what we do is we assign each of these values the corresponding digital level. So for example, this value is between 0 and 0.625, so it is assigned a value 0, 0, 0. Similarly, let's say this value, it is given a value 1, 0, 0, and so on and so forth. Okay. So this process of kind of assigning each analog value a particular digital level is called quantization. After you do quantization, your signal, and if you join the signal up, would look something like this, right? Because, well, I should have had a line here as well, which I think I made a mistake here. But you can see that this point is approximated by this level, this point is approximated by this level, and so on and so forth, and you get a value like this. And if you compare it with your analog signal, you can see that the signal is, well, it's a reasonable approximation of the analog signal, this sampled and quantized signal, though it has some errors.